All right, go ahead, Mark. All right, welcome back, everybody, to this week's installment of the GOCC. We're very excited to have Benjamin Janey from the University of Kentucky with us this week. Before we get started, I want to remind everyone of our community statements, which are the guiding principles that we have here at the GOCC. An expanded version of these is on the GOCC website. But just to give you an idea, our three main principles are that we are all learning, everyone has something to contribute, and no one has all the answers. So if you have questions at any point during this talk, feel free to ask them or put them in the chat, and we will make sure that we ask Ben those questions. So without further ado, please welcome Benjamin Janey from the University of Kentucky, telling us about a critical theorem for q-matroids and rank metric codes. Take it away, Ben.
Thank you, Katie. Thank you for the organizers for inviting me. I'm excited to present some of my work that I've done through grad school here. And so before I get started, while I have everyone's attention, I would like to promote the Spectra conference that we're hosting at University of Kentucky in May, I believe. So Katie put the link to the website on the chat. I want to emphasize that we do have money for travel funding. So you really can apply for that, and please apply for that. And I hope that I will see some of you at the conference in May. And that conference really promotes LGBTQ+ community in mathematics, especially for grad students and young researchers. Okay, so that being said, now I can go to my talk and to discuss this critical theorem for q-matroids and ranked metric codes. So let me give you a little motivation behind this work. So matroid theory was originally defined to generalize the notion of linear dependence. And matroids have been found to be useful in many areas of mathematics, including coding theory. Because a code under, so a code is a subspace under the Hamming metric, induces a matroid, and that matroid captures many invariants of that code. And one of the most celebrated results is the critical theorem established by Crapo and Rota, which roughly speaking states that the number of t-tuple of code words, so element of my codes, with a given support can be fully determined by evaluating the characteristic polynomial of the induced matroid. So it's a really strong tool that allows to relate coding theory to matroid theory. And so in recent years, q-matroids, which are the q-analogue of a matroid, were found to be really useful to study those ranked metric codes. And it was found, as people kept studying them, that the connection between q-matroids and ranked metric codes is really similar than the connection between classical matroids and linear block code. And so one natural question is, can one determine a critical theorem for q-matroids and ranked metric codes? And so that's what I'll be discussing. So before we get into that, let's look at the classical case and really let me define what a linear block code is, and then we'll go into the relation to matroid theory. So here I'll be dealing with spaces over finite fields. So FQ denotes a finite field of order Q, right? And so given a finite dimensional vector space over FQ, we can define those different notions. So the Hamming support of a vector V consists of the set of indices I, such that Vi is different than 0. So wherever I is different than 0. Now the Hamming weight of a vector will just be the cardinality of the Hamming support. And the Hamming distance between two vectors will just be the Hamming weight of the difference between those vectors. And so this Hamming distance is really a metric. And so we say that a linear block code is a subspace of this metric space under the Hamming metric. Okay. So something nice about those linear block codes is just a space of vectors, so we can represent any code by a generating matrix G, where the row space of G will be the code that we're considering. And that will be key for the rest of the talk. Okay, so how are those codes related to matrix? Let's first define what matroid is. And so a matroid can be defined via a rank function R on the collection of subsets of a finite set S to the integer values. Okay, so S is called the ground set of a matroid, and R its rank function. Now, this rank function needs to satisfy three properties. It needs to satisfy a boundedness property. So for any subset A of S, the rank of A, so R of A, must be between 0 and the cardinality of that set. The function also needs to satisfy some non-decreasing property given by R2. And the most important one is that the rank function needs to satisfy this submodularity property, which states that so the rank of the union of two sets plus the rank of their intersection must be less or equal to the sum of the ranks. Okay. So now that we have the definition of matroid, how do we induce one from a linear block code? So the key is, or one easy way is to consider a generating matrix for our code. Okay. So this matrix will be a k by n matrix, and we will define the rank function on the collection of subsets of 1 through n, where n really represents the number of columns in my matrix, where the rank of a subset A of 1 through n is just the rank of the submatrix G sub A that consists of selecting the columns of G indexed by the elements of A. Okay. And one can check, and it's well known that this function R really satisfies those three properties. Okay, so let's look at a quick example. Let's start with a code generated by this matrix G that has entry in F2 to the 5. Okay. So the matroid induced by G will have ground sets 1 through 4, because 4 columns. And if I were to find, for example, the rank of the subsets 1, 2, I would just select the first and second column and look at the rank of that submatrix over the field of our original matrix. Okay. And so we can see that the rank of 1, 2 is equal to 2. And if we were to check all the different rank values, we would see that the rank function satisfies this nice equality here. Okay. And those are called uniform matroids when you have this nice equality for the rank function. And those uniform matroids are really closely related to a class of codes called MDS codes. Okay. Okay, so now after this example, let's look at a few notions and operations we can do on matroids that will be useful. So given a matroid M, we can define deletion and contraction by a set. So the deletion of M by a set S will consist of the matroid that restricted to the complement of S. Okay, so the ground set of this deletion will be the complement of S, and its rank function will just be the same rank function as our original matroid, just restricted to the subset of the complement of S. And now the other operation of contraction is so the matroid M contracted by S has for ground set the complement of S as well. And now its rank function is defined as below. Okay. And so those operations of deletion and contractions are actually really closely related to operations we can do on codes as well. And those operations are puncturing and shortening. I won't go over what those are, but what I really want you to see is how really the interaction between matroids and codes is really tight, right? So yeah. So now that we define those operations, let's look at the characteristic polynomial and the critical theorem by Cropper and Rota. So the characteristic polynomial of a matroid is the following. We take the polynomial where we sum over all subsets of the ground set of those terms right here. Okay, so it's a polynomial in one variable. And so using this characteristic polynomial, we can get a lot of information about the code, about a code that induces a matrix. And so the critical theorem by Krapper and Rota states that for any given code C and its induced matroid M, then we can determine the number of t-tuple of code words, so elements of C, that have given support A by considering the characteristic polynomial of M contracted by the complement of A, evaluated at q to the t. Okay. So here q really represents the order of the field that our code is defined over, and this power t represents the t-tuples. Okay. So how strong is this result? Well, let's look at a quick example of what it can do. Let's start with this random, so this matrix G, which is an ongoing example here. And let's try to determine how many elements or how many code words of our code have full support. That means how many code words have zero or like have all non-zero entries in it. Okay, so there's no zero in any of those code words. Well, to do that, what we can do is compute the characteristic polynomial of the matroid induced by G and just evaluate it at 2 to the 5th, which is the order of the field our matrix is defined over. And we immediately get by the critical theorem that the number of code words with full support is equal to 91. So you can see from just this how powerful that is by just, if you were just to try to like count those number of code words, well, it would probably take you a while, right? And so here we just have to evaluate a single polynomial, which makes life much easier. Okay. So that's the kind of what we want to generalize. This critical theorem is really what we want to generalize to rank metric codes in q-matroids. Okay. So that being said, let's now look into ranked metric codes. Okay, so ranked metric codes get a little more difficult, and I need to set up a little groundwork first. But so basically, our ranked metric codes will be subspace of field extension of fq of degree m. Okay. So to define the ranked metric, what I need to do is define the following map, which will be called the coordinate map. So given a field extension of degree m of fq, let's fix a basis gamma of fq to the m over fq. Because this is a field extension, we can consider it as a vector space over fq. Okay. Then define this map size of gamma that takes any entry in or any element of fq to the m and expand it as a coordinate vector with respect to that fixed basis gamma. Okay, and we'll look at an example afterwards. So just rest assured. But so using this coordinate map, we can extend that to a map from the n-dimensional vector space over fq to the m to the space of n by m matrices over fq, where we extend each entry of our vector as a coordinate vector. So each entry will just become a row of the matrix, where the row is just the coordinate vector of that entry with respect to the basis gamma chosen. Okay. And so we will call this matrix here, this n by m matrix associated to any vector in fq to the m to the n, the coordinate matrix with respect to the basis gamma. Okay. So using this map, we can define now similar notions for the rank metric, or similar than what we did previously for the Hamming metric. So given any vector in fq to the m to the n, and a fixed basis of fq to the m over fq, we define the rank support of a vector v to be the column space over fq of the coordinate matrix of v. Now the rank weight of our vector v will just be the rank over fq of its coordinate matrix, and can also be seen as being the dimension of the support, the rank support of that vector v. And using the rank weight, we can define the rank distance, where the distance between any two elements will just be the rank weight of the difference between those vectors. And so an fq to the m linear rank metric code will just be a subspace of fq to the m to the n with this rank metric. Okay, and here I specify fq to the m linear rank metric code because one can generalize this notion of rank metric to spaces of matrices, where the rank metric will just be the rank of the difference between two matrices. Okay, but unfortunately, those more general rank metric codes do not induce q-matroids, and so for my talk, I need to restrict myself to those classes of codes, right? But so what's nice about those rank metric codes here is that since they're spaces of vectors, we can represent any code via generating matrix as well, which will be useful when deriving a q-matroids for those. And I should also say that notice that in each of those definitions, we had to fix a basis of fq to the m over fq. However, it's well known and not too bad to show that all those notions are actually independent of the basis chosen. So we really can choose any basis we want, and the rest of this notion is well defined. Okay, so let's look at a quick example now after all those definitions. So let's look at a vector of f8 to 3 here, where we consider f8 as being a field extension of f2 of degree 3. So we fix a basis of f8 over f2 as being 1 alpha alpha square, where alpha cube is given by this relation here. And then let's just select a random vector v from our space. Now the coordinate matrix of v here, I need to rewrite each entry as a coordinate vector. So this first entry 1, with respect to this basis gamma, its coordinate vector will just be 1, 0, 0. Now the entry alpha its coordinate vector will just be 0, 1, 0. And one can see that alpha plus 1 just becomes 1, 1, 0. Okay. So now what is the rank support of this vector v? Well, it'll just be the column space of its coordinate matrix, which is just a two-dimensional space generated by those elements. Okay. And then the rank weight of v will just be the dimension of its support, or the rank of its coordinate matrix, which is just 2. Okay. So hopefully that helps illustrate a little bit what this rank metric is, and what this notion of support is as well. Okay.
I have a question.
Yes. Yeah.
So you said that eventually we're gonna find out that these are basis independent in some sense. But the way I kind of understand, well, I was trying to mentally come up with definitions. If we go back a slide.
Yeah.
So for rank distance for me is kind of like the minimal number of basis vectors you need to do to move from B to W, or vice versa. And so it feels like if I just choose V minus W as one of my basis vectors, then I can always get a rank distance of 1 between any two vectors. Does that fail for some reason? Am I missing something here?
Here you're really choosing V and W to represent, like, to have just one, like, like it's not always true that like the distance between any v and w is gonna have rank distance 1. If I'm trying to so you said you let v be, but v, okay.
So it may be that for a particular V and W, I can choose some basis so their rank distance is 1, but I can't do anything below. I can't make it so that for every V and W, that would be
Yeah.
okay.
Yeah.
I think I understand how this meshes with your previous comment.
Yeah. And really, okay, what's different too is for the support, we're not taking the row space, like basically, okay, that's where it gets like pretty tricky. Like those vectors, like when we take their coordinate matrix, they like we expand them as a row, right? But then we take not the row space between
Okay.
to find the support, we really take the column space.
Okay.
And also,
I cannot do that in my head.
Yeah. So a different way to define the rank support without having to deal with this coordinate matrix is take the span, the dimension of, take the span over FQ of all the entries in your vector.
Okay.
Okay. So you'll have entries in FQ to the M, right? But then just consider those as just like the span over FQ, and so like, yeah.
Okay.
I don't know if that helps a little bit.
I think it does.
Okay.
Thank you.
Yeah. Yeah, that rank metric is a handle to grab. It took me a while to like really like, it gets really confusing because you can constantly change from FQ to the M to FQ. But yeah, okay. Okay, example. Okay, so now that we've looked at rank metric codes, let's see what a q-matroid is and how can we derive a q-matroid from a rank metric code. So q-matroids can really be seen as a q-analogue of matroids and are really defined in a similar fashion, where we can define a q-matroid via a rank function that now goes from the collection of subspaces of a finite dimensional vector space over a finite field. Okay, and so this rank function satisfies really the same analogous properties as for matroids, but we really replace the set terminology by its q-analogue in the, so as like all set terminology by just vector space over finite field terminology. Okay, so for example, for any subspace of E here, our ground space E, the rank of that space V must be between 0 and the dimension of V here. So now instead of considering cardinality of sets, we consider dimension of spaces. Okay, we still have like a non-decreasing property and still have a sum-modularity property for our rank function that now states that the sum of two spaces plus the intersection of this, so the rank of the sum of those spaces plus the rank of their intersection must be less or equal to the sum of the ranks. And so you can really see this sum and intersection now as being like the operation of the lattice of subspace of a vector space, right? Okay. Okay, and so how do those q-matroids arise from codes, rank metric codes? Well, we can use a generating matrix for a code to do so as well. So let G be just your generating matrix of a code, and we will, so G will have n columns, and we will consider the code to be a rank metric code. So we really consider, so G is defined over FQ to the M, but we consider FQ to the M to be this field extension of degree M over FQ, right? So this rank function will be defined over the collection of subspace of FQ to the N. And for any subspace of FQ to the N, the rank of that space will just be the rank over now fq to the m of G times a matrix that generates our space V. Okay. And so it was shown.
This matrix, where is this matrix coming from? Like YV?
Why? So
just
Y sub
any
V is
matrix?
just a choice of matrix, such that the column space of that matrix is the space V that we're considering. So you can really
Thanks.
choose any, as long as the column space of this Y sub V generates V, you can choose any choice of such a matrix. Yeah, thank you. Okay, and so it was shown, and now it's well known that this rank function satisfy those three properties. Okay, so let's look at a little example, ongoing example of this matrix G. Now we consider G to generate our code over f2 to the 5, right? And where f2 to the 5 is field extension of f2. And so we define the q-matroid that has ground space f2 to the 4, and the rank function as defined below. And if we were to, for example, find the rank of this two-dimensional space generated by those two elements, we can put those elements as column of the matrix Y sub V, right? And multiply G to this Y sub V, which would just give us this matrix right here. And now to find the rank of this space, we just take the rank over f2 to the 5 here of this product of matrices. And that would give us 2. And similarly for this case, if we were to check all the rank values, we would see that the rank function is really nicely defined, and it's called a uniform q-matroid now. And similarly to the classical matroids, those uniform q-matroid are closely related to a class of rank metric codes called MRD codes. Okay, so there's really still this connection between coding theory and matroid theory happening here. Okay. Now, similarly, then for matroids, we can define the notion of deletion and contraction. Now, deletion gets a little tricky because we have to make the choice of some inner product, where now we restrict our q-matroid. If we delete by a space V, we restrict our q-matroid to the orthogonal space of V. Okay, and the rank function really stays the same. We just restricted our ground space. Now the contraction of V, so M contracted by V has for ground space the moduli space E mod V. And for any subspace of this ground space, its rank is given by the following formula. Okay, which is kind of similar to that contraction of matroid that we looked at before. Okay, and similarly then for matroids, this notion of deletion and contraction of q-matroids behave really nicely with the notion of puncturing and shortening of rank metric codes. So we once again have still this really nice connection between q-matroids and rank metric codes. Okay. Okay, and similarly then for matroid, one can define the characteristic polynomial of a q-matroid in the following way. So now we sum, the characteristic polynomial is just a sum over all subspaces of the ground space of those terms right here. So you can see those coefficients get a little messier, but those are actually the coefficients or their values of the Mobius function on the lattice of subspace. That's how we get those coefficients right here. Okay. And so, as we've seen so far, there's really like many of the information we saw from classical matroid theory seem to extend to q-matroids and rank metric codes, right? So one question is, does this characteristic polynomial give us the same type of information about the q-matroid that arises from codes, right? can we relate the notion of supportive codes to this characteristic polynomial? And also, with all those connections that we've seen, can we somehow relate the characteristic polynomial of a q-matroid with the characteristic polynomial of classical matroids? Okay, and that second approach is really what I wanted to do is really create more explicit connections between classical matroids and q-matroid. Okay, and we'll see how those connections play a role here. So in order to find this connection, let's define a few notions, flats and loop, and we'll see really nice properties about the characteristic polynomials using those notions. So a flat of a matroid is just a subset of the ground set, such that adding any element to that set necessarily increase the rank. And now a flat of a q-matroid is the same, defined similarly. They're just subspaces of the ground space, such that adding any additional any extra one-dimensional space must increase the rank as well. Okay, and a loop of a matroid or q-matroid is either an element or a one-dimensional space that have rank 0. Okay. So for those flats, so the collection of flats of both matroid and q-matroid have really nice structure. They end up being lattices, and in fact, they both end up being geometric lattices. Okay, and we can use those flats to actually study the characteristic polynomial. So that's a theorem by Whittle that showed something in more generality. But when we restrict to matroid and q-matroid, state the following: that if you have a matroid or a q-matroid, and that do not have any loops, then you can express the characteristic polynomial in terms of the lattice of flats. So here, this mu is the Mobius function of the lattice of flats. You don't really need to know what the Mobius function is. What I really want you to get from this slide is that the characteristic polynomial only depends on the flat structure, right? For both matroids and q-matroids. And now we have that case where if either our matroid or q-matroid has a loop, then we know that their characteristic polynomial has to be identically 0. Okay? But so this connection is quite crazy, because it tells you that if you have a matroid and q-matroid that have a similar flat structure, then their characteristic polynomial have to be equal to each other. Even though the way we define characteristic polynomial, those coefficients seem quite different, and it didn't make much intuitive sense on that they should be equal to each other. And so what we'll do is really to relate characteristic polynomial of matroids and q-matroids. What we can do is for any q-matroid, find a matroid that has the same flat structure, and we'll be able to relate those two objects to one another. Okay, and so this leads me to introduce this projectivization matroid. It is a matroid that can be induced associated to a q-matroid. So this was defined by Johnson, Pratillard, and Verdure. And so start with the q-matroid, then what we'll do is define a rank function on the collection of subsets of the projective space of fq to the n. Okay, where here the projective space is really the set of one-dimensional spaces of fq to the n. And so for any subset of pfq to the n here, the rank of that set will just be the rank of the span of that set in the q-matroid we started with. Okay, and by span, I mean really the smallest vector space that contain all one-dimensional spaces of S. Okay, and so the authors were able to show that this rank function is really the rank function of a matroid. Okay, and so this P of M is called the projectivization matroid. And so I give a little example here. If I start with this q-matroid with this rank function, then the projectivization matroid will have for ground set the projective space of f2 to the 3 and the rank function as defined above. And if we were to find the rank of the set A here, we need to find the rank of the span of that set A, that is the smallest subspace that contains A, which is just a two-dimensional vector space or two-dimensional subspace, right? And so based on the rank function of the q-matroid we started with, we know that the rank of A is just 2. Okay, but so why is this projectivization matroid so nice? Well, it turns out that this projectivizing process preserves the flat structure of the q-matroid. And it's really, one can show that the flats of our projectivization matroid will just be the projective space of each flat of our q-matroid. Okay, and so it really preserves the entire lattice structure. And because of that, we can, and because of this characterization of the characteristic polynomial in terms of flats, we know that the characteristic polynomial of our q-matroid is equal to the characteristic polynomial of its projectivization matroid. All right. Okay. So let's go back to the critical theorem really quick and look at the statement, right? For classical matroid, we need, so for classical matroid, what we need is a characteristic polynomial. We need to understand how the characteristic polynomial behaves under contraction. And what we also need is a code to induce the matroid that we're considering, right? So our goal here is to use this projectivization matroid to study or to find an analog of the critical theorem for q-matroids, right? And so what we need to find is how the characteristic polynomial of the q-matroid and its projectivization matroid behave under contraction. And we also need to figure out if I start with a q-matroid induced by a code, will its projectivization matroid also be induced by some other type of code, right? And so that's the two kind of pieces that we'll try to get together and then look back at this critical theorem later on, okay? Okay, so first start with contraction. So contraction behaves really nicely, okay? So if I look at a q-matroid and its projectivization matroid, then if I contract M by a flat V and P of M by the projective space of V, then I preserve the equivalence of the lattice of flats. Okay, those two lattices of flats will still be isomorphic. Now, if I do not contract by a flat, so if I do not contract M by a flat, then both M contracted by V and P of M contracted by P of V will contain loops. And so that will make our character, since, so they will contain loops. So using those two pieces of information, we can now relate the characteristic we see that characteristic polynomials of the q-matroid and projectivization matroid behave well under contraction. Mainly that if I contract M by V, I use the flat structure to figure out that those two characteristic polynomials are equal to each other. And if I contract, if V is not a flat, then I use the fact that both M contracted by V and P of M contracted by P of V contain loop to say that both of them are equal to 0. Okay, so this little structure result really allows us to establish this property regarding the characteristic polynomial under contraction. Okay. Okay, so we know this behaves well under contraction. Now let's look at whether there exists a code that represents our projectivization matrix. And that's where a construction by Alfarano, Boello, Neri, and Ravagnani came into play. So in their paper, the authors associated a linear block code to a rank metric code. Okay, and they use finite geometry arguments to do so. And here I provide a little construction that just involves matrices and linear algebra to provide an equivalent type of code. Okay. So what we'll do is start with a rank metric code C generated by this matrix G and associate a linear block code to it, which we construct in the following way. So we build a matrix H, which consists where each column of H represents a one-dimensional vector space of fq to the n. Okay. And we call the product between G and H. So the code induced by the product of G and H, the Hamming metric code associated to C via H. So notice how this code, so this matrix G times H, and so this code really depends on the choice of H. However, as you vary H, you get equivalent codes. And so for our purposes, that's not a word, okay? But so a quick example, if I start with my matrix G, define as follow, and define over F2 square, then what I'll do is construct H to list all the one-dimensional spaces of F2 to the 3. Okay. And so the Hamming metric code associated to G via H will just be the product of G and H, which is given here. Okay. And so this code really is quite nice because it preserves a lot of structure. So this linear block code preserves a lot of structure from the rank metric code we started with. Okay. And so we really study this Hamming metric code associated to C under the Hamming metric. Okay, we study the rank metric code under the rank metric, and we study this code under the Hamming metric. Okay, but why is this code so nice? Well, it turns out that if I start with the rank metric code C and look at its induced q-matroid, then any Hamming metric code associated to C will induce the projectivization matroid. And so that means that we have this really nice relation between projectivizing the matroid and also kind of projectivizing the code. See that this projectivization process really follows also on the coding theory side. Okay, and that will be extremely useful. That is extremely useful for the critical theorem that we're trying to show. Okay, and we can say even more about this Hamming metric code associated to C. We can nicely relate the rank supports of elements of our rank metric code C with the Hamming support of elements of the associated metric code, the associated Hamming metric code CH. And in order to see that pretty easily, what we do is relabel the columns of CH here, where the ith column, we relabel the ith column of CH as the one-dimensional space generated by the ith column of H. And so using this relabeling, we have this nice characterization, a relation between the support, the rank support of code word of C with the Hamming support of code word of CH. Okay. Okay. And so that gives us really all the information we need to prove a critical theorem for rank metric code in q-matroids from a purely classical matroid approach. So here's the statement of that theorem. So given rank metric code C and its induced q-matroid, then the number of t-tuple of code word of C that have a given rank support W can be determined by evaluating the characteristic polynomial of M contracted by W perp, evaluated at Q to the MT, where here Q to the M represents the order of the field our code is defined over, and T once again represents the t-tuples. And so how does this proof go? Well, let's go through the projectivization matroid. So I know that if my q-matroid M is induced by a code, then its projectivization matroid is also induced by a linear block code. So we can apply the classical critical theorem to the projectivization matroid and it's the code that induces it, right? And so that gives us the following equality right here. Okay, that's really the classical critical theorem. But so now using the tools that we had, we know that the left-hand side of this equality here can be rewritten in terms of the rank support of the rank metric code we started with, meaning that any set that should be v times h, sorry, a little typo. So any set v times h that has Hamming support projective space of W perp is in bijection with the sets of V, so of code words of C that have rank support equal to W. So I can replace this left-hand side by just the left-hand side of the stated theorem. And now for the right-hand side, for this characteristic polynomial, well, we saw that the characteristic polynomial behaves well under contraction, and that this characteristic polynomial of PM mod or contracted by P of W perp is in fact equal to the characteristic polynomial of M contracted by W perp. And so I can replace the right-hand side of this equality by just the right-hand side of the stated theorem. And that just proves our q-analogue of the critical theorem by just considering the classical case. And so I should say that independently, Alfarano and Bjorn showed a similar theorem using a different approach of Mobius inversion. And so, yeah, their paper is not out yet. So, yeah, and I'm not sure when it'll be. But yeah, so let's look at the power of this q-analogue of the critical theorem. Let's start with our ongoing example. So G generates our rank metric code. And we want to figure out the number of code words that have support F2 to the 4. Okay. Well, what we can do, instead of just counting one by one, is compute the characteristic polynomial of the q-matroid induced by G and evaluate that characteristic polynomial at 2 to the 5th, which gives us 19,592, which would be quite long to just compute one at a time. And so, yeah, it's really nice to see that that works out for rank metric code and q-matroids. And so, yeah, and so as a conclusion remark, so this approach I took really shows that this critical theorem for q-matroids and rank metric codes is really a specific case of the one for classical matroids and linear block code. And the same hold for this critical problem. The critical problem is given a characteristic polynomial of a matroid to find the smallest power of q that makes that characteristic polynomial greater than 0. So one can ask the same question about state the same problem for q-matroids. Well, it just turns out that that problem will just be a specific case of the critical problem for classical matroids. And I should say also that this projectivization matroid is really useful to study the characteristic polynomial. It allowed me to show a deletion contraction formula for the characteristic polynomial of q-matroid, which would, at least for me, would have not seemed obvious at all without having to look into this projectivization matrix. Okay. And so I think this relation will be quite nice in the future to get more out of those characteristic polynomials in the theory of q-matroids. And so, yes, I thank you for your time. Here are some references. And if you have any questions, please feel free to ask.
All right, let's thank Ben. Very nice. And open up the floor for questions.
I have a question. Can you go back to when you were talking about deletion and contraction for the q-analogue of matroids?
Yeah, thank you.
Yes.
Okay, what is E here? Like, what is your ground set?
So it's just a random, like an abstract finite dimensional vector space of FQ.
Okay, okay.
So yeah, the problem is we don't want to restrict to just like FQ to the n, for example, because you see like here in the contraction, right, we have to use like moduli spaces. And so for that reason, like we wanted to abstract just a little bit more and just define E as, yeah, just being a random vector space, basically.
Okay.
But yeah, it's like you can replace E by FQ to the n and that works, yeah.
Okay, cool.
Yeah.
Thank you.
Okay, I'm formulating a question. I'm not sure if I know how to ask it, but I'm gonna try anyway. So whenever I see people talk about like all of the subspaces of a space of fixed dimension, I think about the Grassmannian, which is over an infinite field though, right? Is there any connection that you know of here between like what you've been doing with finite fields and codes that like could be related with infinite fields? Or is that even a question that is askable?
No, that is a really good question. I think so. In the original definition of q-matroid, I don't think you do not need to restrict to finite fields.
Okay.
So you could define q-matroids. No, okay. Okay, that's where it gets tricky. I think I'm not entirely sure. I think you do not need to restrict to finite dimensional vector space.
Okay.
You might need to restrict to finite fields. There might be issue with just like defining all of that for like just random infinite fields. But
That's totally fine.
yeah. But that's a great question. I have not looked at it, to be
That's
honest.
totally fair.
But yeah, no, that's pretty interesting. Yeah. Thank you for asking.
Yeah. All right. Other questions? Right. If not, I have maybe one more. Sorry. One more like maybe it doesn't have an answer question. Any like hope that you have about like what you can now say about the characteristic polynomials now that you have your critical theorem? Anything you want to try to prove?
So not off the top of my mind, to be honest.
Sure.
Because I haven't really looked back at that since I finished that project.
Yeah.
But I mean, I know some people, I mean, what would be interesting is really to try to figure out this critical problem for ranked metric codes and q-matroids. Because I mean, it's really like a subclass of the critical problem for classical matroids. And so it might be possible to solve this problem or to like have a better understanding for q-matroids.
Nice.
But yeah, and then one can define like other types of polynomials, for example, the Tud polynomials, the Tud polynomial. And so some people, so Bjorn and Falker, also the q-matroid theory, define an q-analogue of the Tud polynomial,
Nice. Okay.
but it does not seem to behave as nice, like as it does not seem to behave well with the q-matroid structure, like as nicely as like the Tud polynomial of matroids, or like Tud polynomial and matroids behave well with each other, basically. But so that's also like something pretty interesting. But yeah.
All right, well, if there is nothing else, all right, let's thank Ben one more time. And thanks everybody for coming.
Thank you. And thanks again